Hello.
There you go.
And
Okay.
now we have to learn
We've
to
been trying to figure out
Have
for years.
more.
It's being recorded.
I don't know that you're claimed as
to record it.
host.
oh you have to
Yeah,
claim
so
it.
I can claim the host because I know the code.
Oh, so I have to make you the that was
Is mine? Oh,
No, that's mine.
You are, but it doesn't matter.
It's not as late as us.
Maybe I could be that. Or maybe that's
It's mine. I brought some.
So we have to do this every time we have to stop the recording.
Yeah.
I'll give you the
Cool. All right. Cool. So I've talked here a couple of times about some of the research that I've been doing with Suggest here. And in the course of doing this, we've come across some interesting, more or less observations. We don't necessarily have explanations for them, but they seem to be a little too good to be interesting coincidences. So I kind of wanted to present some of what is going on there. This is not the most prepared presentation, just because I've been extremely sick for the past week. So bear with me. But I do have some notes. So the thing that we're mostly interested in is we're interested in a method of re-representing elements of Lie algebras with the algebra of harmonic oscillators. And so I'll kind of talk about what the algebra of a harmonic oscillator is. Like, what does that even mean? Cool. So when we're talking about the harmonic oscillator, specifically, we're talking about it in quantum mechanics, we have an associated kind of operator algebra that appears from that. I'm not going to get into the real like guts of functional analysis or anything like that, but kind of talk about what operators we're dealing with and everything. So the harmonic oscillator has discrete energy levels. A common way of visualizing this maybe is like a ladder where I have my base energy level and then, the added energy levels. Typically, these are the energy levels are h bar omega times n plus 1/2, where n is non-negative integers. Right, so 0, 1, 2, so on and so forth. These are the measurable energy levels we get from the harmonic oscillator. Harmonic oscillators, think of like a spring with a mass on it and stuff like that. And so we've got a base state, which I can label just with 0, right? This is just this number right here. It's how we label our number states. My first excited state, second excited state, so on and so forth. And I can move between these energy states, right? I can act on this state to then give me the state that when I measure the energy is the next excited energy level. And you think of these kind of like arrows going up and down, where going up is with a dagger, going down is with an A. So I'll kind of write it out explicitly. If I have a state in, I can either go up, so a dagger on n. This is square root of n plus 1 on n plus 1. That's just a normalizing factor here. And then a on my state, lowering it, gives me square root of n on n minus 1. Cool. So this is mainly what's going on, and we have a couple of things. We're mostly focused on commutation relations. In quantum mechanics, the commutation relation is like the generalization of a derivative. Like it talks about how an object changes with respect to another object. So our commutation relation, this is just the standard commutator bracket, xy minus yx. This is an interesting quantity to look at when we're talking about operators of systems, like systems of operators. So the important commutation relation I get here is a dagger equals the identity matrix, right? These are operators. They can be realized as matrices. their commutation is a matrix, right? That's a matrix, that's a matrix, I get a matrix. So here's the identity operator is my result there. Cool, cool. And this comes from specifically, or the important one to realize is that the operators for the observable quantities of position and momentum is I, H bar, and then the identity there, right? So these are also linear operators. So the result's a linear operator, and it's the identity scaled by IH bar. This is like almost an axiom of quantum mechanics, right? Quantum mechanics is described as a theory of certain things. This is one of the things we require, is that in whatever basis we're dealing with, that these operators specifically commute here.
So what comes first, these relations or X and P?
X and P are more fundamental. This is like a fundamental commutation relation. A and A dagger are built from this X and P. So A is, it's got this nice factor out here, H bar omega M, and then I, P plus M omega X. And then A dagger is Q H bar M omega minus IP plus M omega X. This basically just comes from when I study the energy of the system, I get the Hamiltonian of it. And it's almost like kind of factors the Hamiltonian. If I remultiply these, I get the Hamiltonian scaled a bit, and then this like number factor here. But this, I've got this P and this X here. When I remultiply them together, that's where I get this commutation right here.
So from these commutations comes the top, like N goes to those two states, right?
Yes, yes.
So that would be the right order, because somebody like looking first time sees all this at the top.
Mhm.
This one A and the plus comes from the
Yeah,
top, but it is the other way around.
maybe highlight this goes here. And these don't exactly come just from this. They actually, well, they do come from this. And then we also create the number operator, which is called N, such that when it acts on my state, this is the same thing as A dagger A acting on my state, which gives me just the number. It reads out the number. So basically, it's proportional to the Hamiltonian. So it's proportional to just reading off the energy. It's doing the same thing here. And so this has commutation with these things right here. They have their own algebra of commutation. Right. This commutation is what gives me this like raising and lowering type of thing right here. Cool. So that's the kind of algebra that we're working with. And it's of interest to note what Pascal Jordan was doing here. So I'll write his name here. 1935, Pascal Jordan. He's a German theoretical physicist. He's mostly working on studying the solutions of the quantum many-body problem. And what he recognizes is that when we're talking about these operator methods are useful for talking about the quantum many-body problem. He recognizes that there's a connection between these and the behavior of Lie algebra elements. So specifically, I'll kind of doodle this a little bit. What we're talking about here is we're talking about a collection of harmonic oscillators. I can keep going, and I can label them differently. If this system has maybe in A, right, it has A operators and a number A that we associate with it. Each of these might have like a number 1, a number 2, so on and so forth. So they're all described independently, such that this has, an A1 dagger and an A1 that goes up and down. This has an A2 dagger and an A2 goes up and down, and its own states. This might be in A1, in A2, so on and so forth. So I have my independent stuff here, and they all individually have this algebra, but are disjoint with each other such that like the operators don't commute. So there's no change with the operators. I want to say specifically like AI AJ dagger is delta IJ. So they only give you your one identity operator if you're talking about the same space. So if you're talking about, A1s with A1s or something, they give you 0 if you're talking about two different spaces. So we're talking about disjoint harmonic oscillators, the algebra of these.
Do you mean like times the identity matrix or anything?
Well, this
Those are
is an
matrices,
operator.
that's a number.
So
Oh, sure.
yeah, that's an operator. It's this itself is the identity matrix. So, but yeah. I'm gonna leave that statement as that.
Good.
So can you say this is just direct product of these algebras?
What do you mean the product of the algebra?
Product, or like a product of two algebras. They don't interact, but you have higher dimension.
Oh yeah. When we yeah, exactly. When we go to talk about the representation of higher dimensional spaces, we talk about the product of these, and so that's what I'll be doing here. Cool. So we have all this machinery, and I'll leave the important results out that we want to remember when we start talking about some interesting results. And I guess the main important one really is this AI AJ dagger is delta IJ. That's like really the one that we're focused on here. So Pascal Jordan was looking at this. He was looking at these operators, and these were the operators he was using. And he identifies this kind of way of constructing another kind of operator. I'll call it AAL, where these are just like kind of indexing. They tell you what basically harmonic oscillators I'm talking about. And he gives it as A dagger K, AL. So K and L can be whatever. It just depends on the size of space that I want to represent. I'll first deal with the case of a two-dimensional space. So K, L are in, we'll say 1 and 2. So I'm just talking about two spaces. And he identifies that this kind of construction here behaves up to 3 different conditions, the exact same way that the basis elements of the general linear group do. So what are the basis elements of general linear group? Let me first talk about that. The general linear group of n by n matrices is just n by n invertible matrices, right? They're representations of linear operators on an n-dimensional space. So I want to talk about specifically GL2 because it'll be of use for us to represent SU2. That gives us a representation of angular momentum, which is what we want to deal with. So we have 2 by 2 invertible matrices, and there's like 4 basis elements essentially. And I can
GL2 algebra or group?
talking about the group first. Yeah, I'm talking about the group. Any element of the group can be generated by one, like a linear combination of these. So these span the group.
This is over C, right?
Yeah, where's the
just any field. C to be general.
Your
But
second matrix is not part of the group. It's not inverted.
It means the algebra.
okay, then I am talking. Yeah, I'm talking about the algebra.
That's what
And this is the algebra, it generates the group. That's what we're talking about. Thank you. So any element of GL2 is made of a linear combination of these. So this algebra right here generates the group. So these are in the algebra GLN, or specifically GL2. And their linear combinations form the elements of GLN specifically.
small GLN, right? Just make sure.
Yeah, the GL2 here. Cool. And so specifically, these elements, I call them EKL. This means that it's a 1 in the kth row L column, and it's 0 otherwise. So for instance, this is E11, E12, E21, and E22. Cool. And what Pascal Jordan showed in his paper was that these AKL behave the same way that these EKL do with some certain considerations. So what are the things we want to consider? One thing to note of these EKL is that EKL, EJM, for instance, so if I'm multiplying two of these elements together, I get delta JL EKM. So I only get an element if, these inner parts agree, and then that element's position is located there. So if I were to multiply, say, these two together, I get 0, right? Because these don't agree, but I can multiply these two together because this 2 and this 2 here agree, so on and so forth. That then lets us talk about the commutation of these. EKL, EJM, that's delta JL EKM minus, and then delta NK EJL. Cool. One thing that I noticed with these is that with this commutation relation, I get the same thing. I do AKL with AJM. I also will get delta LJ AKM minus delta around, so MK AJL. I can explicitly go through and show that out. So that's one way that they're the same, which you noticed. What was the other way? Another thing is that EKL, I take the Hermitian conjugate of this, so that's the transpose and the complex conjugate. These are all ones, so it's just going to be the transpose there. So I get ELK. I get the same thing over here. I get AKL transpose is ALK, right? I can show that explicitly. This is AK dagger AL. Transpose that, I get AL dagger AK. Daggering twice gets me back to the same thing, and that is ALK. So that's the second thing that he wanted to highlight. And then another thing that he highlights is that if I add up the diagonal elements, like basically taking a trace almost, I get whatever the dimension of the space is here. So specifically, sum over K EKK equals N. Here, N is going to be 2. I'll do specifically for this example 2, right? And when we're talking about these operators, we get the same thing. We get, when we're talking about the spaces, maybe draw this out. Right. These individual spaces have their number operators. That number tells you basically how much, or in a way, it tells you like how many particles are in the space, or like the excitation level, or something like that. And if I add up sum over K of these, I also get my number N, right? Specifically, let me take it here. N as a whole, when I'm considering multiple of these together, is the sum of the individual, like N1 plus N2. Since I'm just talking about a two-dimensional space, I'll talk about these. So this would be A1 dagger A1 plus A2 dagger A2. That gives me my number N. In this case, we're talking about a 2 oscillator system, so my number here is 2. I'm just talking about 2 different things here. So those are the 3 conditions that he highlights to talk about how these essentially are acting as the same thing. And then he presents or doesn't himself in the paper present a way of representing these things. But from this, we gather a way of re-representing elements of Lie algebras. So I don't need this.
Your little model with the arrows pointing up and the dots, is that intended to extend up to infinity?
Yes. So these are theoretically infinite,
Okay.
unbounded in the positive
Yeah.
direction.
Yeah.
So I can take any element, say just of GLN, call it X, maybe as an operator. So this has its elements Xij, and then multiplied by these or I'll do KL since I've been using KL. Multiplied by the basis elements EKL, right? So for instance, if I took 1, 2, 3, 4, this is X11, X12, X21, and yeah, it's purple, X22. And this is just, 1 times this plus 2 times that, 3 times that, 4 times that.
So you mean in this equation, there was a sum?
Yeah, there's an implicit
Yeah.
sum over K and L equal 1 to 2. So yeah,
If you want to use the method of,
then I move them
you have
up.
to move up, yeah.
So yeah. So I can write out it as a linear combination, basically, of all the matrix elements times those. But I showed that those were proportional to these oscillator pair combinations. So I can rewrite this as the sum from K and L equals 1 to 2 of my elements, X, K, L, now times this AKL, which was the same. Sum over K, L, 1 to 2, XKL, AK dagger, AL. Cool. And then because this is just a number, these commute. And so I can write this as the sum, K and L equals 1 to 2 of AK dagger, XKL, AL. Cool. And then when I'm summing over this kind of looks like dot products. Like basically that's what I'm doing. I'm doing like array multiplication here. So in general, what we end up writing is a very short-handed version of it. I let y be given as A1 and A2 maybe, if I'm talking about a two-dimensional system. Here, because I just want to use different notation to emphasize difference, I'll just call this A and B. Right, that's just a relabeling, nothing crazy. And then any operator, X, and emphasize it's an operator, I'll put a little hat on it. I can instead rewrite as Y dagger, where Y dagger equals now A dagger, B dagger. Y dagger, my matrix, I'll put an I here, IJ, and then this is being summed over YJ. Basically like matrix multiplication, so I'll kind of just scrap all the indices and everything. Where here X is the matrix representation of the operator. Yes.
Are A and B also operators?
Yeah, A and B are the operators of the, like this would have like
This would be A1 and A2.
it would be A1 and A2. I just call them A and B.
Sure.
So this would be like B dagger and B. Something like that. We talk about a two-part system. So what's the use? What do I get out of this? Well, the big thing that I get out of this, and this is kind of where most of my thesis work is coming from, this gives me a really nice way to represent SU2, which is angular momentum, right? So I can talk about the elements of SU2. So SU2, or I'll talk more so just in general angular momentum, is there's an X part, the Y part, and the Z part, and I'll actually just use 1, 2, and 3 here. Not restrict myself to thinking in a Euclidean sense. So J1, 2, and 3, And I can talk about a j squared. So just j squared, which is j dotted with j. So j1 squared plus j2 squared plus j3 squared. And then this commutes with all of these, right? I could go through and show, given the defining commutation, ji, jj equals epsilon ij, and there's an I there, I epsilon ijk, jk. Anyone unfamiliar with the Levi-Civita symbol? Just anti-symmetric. Yeah, it's just the anti-symmetric symbol there. So these behave in a cyclic pattern, right? Like J1, J2 equals IJ3, so on and so forth.
So epsilon ijk is the sign of the permutation of ijk?
Yes, yes. That's a very elegant way to put that statement. Yes, the sign of the permutation. So like J1, J3, right? There's an odd permutation there. So I'd get minus IJ2, right? Because I'd be flipping the 2 and the 3 there essentially.
Except when two are equal, this is zero.
And then when 2 are equal, it's
Permutation,
0.
I wouldn't know.
Yeah.
So
It's not a permutation.
Well, right, no.
Yeah.
yeah, it's not a permutation, so it's 0. Specifically, since j squared and j3 commute, they share an eigenbasis. I'm not going to prove that. It's a very kind of involved proof. I'm just going to say that they share an eigenbasis, and I can label it by the eigenvalues. This is j labels the I'll say spectrum, but it's the eigenvalues of j squared, and m labels the spectrum of. So we have these, and we also have ladder operators here too. So I have my j plus, which is j1 plus ij2, j minus, which is j1 minus ij2. They satisfy specifically j plus, j minus equals 2j3, and j3, j plus or minus equals plus or minus, j plus or minus. So those are the important commutation relations there. And then these ladder operators, we call them ladder operators, because they ladder this labeling right here. So specifically, j plus or minus on jn equals some normalization factor out front, and then j and m plus or minus 1. So I also have a ladder where I'm going up or down. It's minus j, and that's plus j. And I've got j plus going up, j minus going down in between these states, where this is, like this, jm, maybe jm plus 1, jm plus 2, and then maybe down to jm minus 2, and jm minus 1 or something. So I'm just laddering between these states such that when I measure, the m component, this third component of angular momentum, I get these values. And so these, for describing angular momentum rotations, these operators are realized as elements of Lie algebra SU2, or the Lie group. No, Lie algebra SU2. Yeah, Lie algebra SU2. So specifically, let me do it here. I have matrix representations of these operators. So J plus has its own matrix representation between this as a basis, 0, 1, 0, 0. J minus has its representation. There's a 1/2 here. No, not for the pluses and minuses of 0, 0, 1, 0. So I've got matrix representations that act on the Lie algebra this way. And so I can throw these into my formula here, basically my construction, and get out what the oscillator representation is. So let me take this space here.
I have a question about, another question about your vertical diagram there.
Yes.
So J plus and J minus, are you viewing these as, let me ask you about the full diagram without the J's first.
Mhm.
Are you viewing kind of each level as some subspace of a giant space?
Yeah, these are the independent dimensions
So,
put into a line.
so you're kind of abusing the notation here. Really, J plus and J minus should act on the whole space. But when you write them as 2 by 2 matrices, you're talking about the restriction to a certain subspace. Is that right?
Yeah, so this would be the restriction to a
And
certain
it
spin
happens to
subspace.
have the same dimension for all of these subspaces on each level.
But
The
there
same
does happen
representation.
to exist, for instance, a 3 by 3 representation of these.
Okay.
It has to do with the spin. So that's like the
Sure.
spin.
Yeah.
gives you-
I just try to piece all this together.
Yeah.
Thank you.
I abuse it for the sake of not only myself,
No,
but
it's just
also the
fine.
audience.
It's fine. I think I just, sometimes I have to ask a clarifying question.
Yeah, you're good. Cool. So I can rewrite this J plus as, well, my Y dagger is A dagger, B dagger. I've got my matrix representation of J plus and my AB. And if I compute all of that out, I end up getting A dagger B. Cool. So this is a method of re-representing this. I could do the same thing with J minus. And I'll say like, how do I use this? Because it doesn't like, what do I do with A dagger B? Like, do I sit it to the side there? What do I do with it? So I've got to actually have something to act on it with. So then I get A dagger there.
To answer the Matthew question, right? There's something else dimension of the space on which algebra acts, and something else dimension of the algebra. So algebra can have small dimension, while the space it acts on can be
Yeah.
infinite.
Yeah.
So these two things should be right confused.
So what do I actually do with these? Like, what am I doing with these? Well, I can act on these, right? These A's and B's are acting on number bases, right? And here I'm really considering the tensor product of these two spaces, right? So they're acting on the product basis, right? I'll just label it in a tensor in B, and the shorthand notation for that is just in A, comma, in B. It's kind of an abusive notation there, but this is the shorthand for the tensor product basis of these two spaces, where each space individually has in A and in B as their bases. And I have the following relationships. J, I'll say is B. I'll say instead. I'll let NA be J plus M. It's the same J and M here. It's these values. I'll let NA be J plus N, M, NB be J minus M. So now there's a proportionality between NA and B and its J M basis. And so I can go through and I can construct and show that this actually does reproduce the same theory of angular momentum in this Jm, the standard basis, using this, what we call the Schwinger basis. So we're just reconstructing it, but instead of using these, this J plus, which I understand the algebraic properties of, I treat this really just with these oscillator pairs of creation and annihilation operators, and then act on it very, very structured, almost like reading out of a book. I go up with one, I go down with the other, and it's as simple as. And then I just basically take it back into this up here. So right, I can solve here. J equals 1/2 NA plus NB. M equals 1/2 NA minus NB. And then whatever I go into from the JM space to the NA and B space, act with these little guys, and then go back into the JM space. And I get a fully working, identical theory of angular momentum. So it's very nice. Just kind of some background on what's being presented here. So I want to revisit.
Any maybe questions or remarks?
Yes, questions or remarks before I get into the.
Well, the crucial point is that it's a Lie algebra, not an algebra.
Yeah, Lie algebra.
Exactly.
The J plus squared is 0. You see, so if you tried to map it and you say, oh, let's look up J plus, remember that's what Matthew's question is, right? You can't just go J plus, it would be 0. There's
Mhm.
nothing going on. Well, that's what your point is, that the dimension of the representation space can be, it's how long those J pluses would have to get bigger and bigger, you know what I mean?
Yeah. So J plus, for instance,
But
like.
it's not an algebra map. That's the crucial point.
Gotcha.
It's Lie algebra.
Lie
It's our favorite stuff. So
Yes,
thank you.
very nice. Very,
So
very
we
nice.
like it. But
A question?
Yeah, so the algebra are J plus and J minus generators of it, or
Yeah, you could, yeah, J plus, J minus, and J3. J3 is proportional to the identity here. Those generate these are the generators for SU2, given these.
Of SU algebra or as
Uh,
algebra? Always have to say.
The algebra generates the elements of the group, correct?
Yes, but
The
you don't touch this thing. You're just talking
Yeah.
only about algebra.
Yeah, so I'm really only talking about the algebra here.
yeah, because like J plus and J minus aren't in SU2, right?
Yeah, like that's a good point. They're not in SU2. Very easy to see, like they don't have determinant 1. That's automatically kicking them out of consideration. So yeah.
J3 is -1.
Oh, there's a minus here?
Yes.
Oh.
Well, at the bottom maybe.
Oh,
Yeah.
there we go. That's what J3 is. Cool.
And it happens to be same thing as an algebra for SL2.
SL2C.
Yeah.
So yeah. Cool. All right.
Special linear.
Yeah.
Rules.
You also have the Jacobi identity, right? Also.
As an algebra, it happens to be.
It does have
All right. So to revisit some of these important commutation relations, just because they led us to an interesting a problem that we kind of encountered here. So with this sort of system, like this re-representation of the operators, like I had J plus is proportional to A dagger B, J minus is proportional to A B dagger. But what happens if I dagger both or don't dagger both? And so the question is there something that's proportional to maybe A dagger B dagger, or is there something that's proportional to A B? And it turns out, yes, there is. I'll call these K plus and K minus. And when I treat them, kind of like I treat these gave me, or were a way of representing or redoing the algebra SU2, which these then give you SU11, the hyperbolic algebra. So we remember, or I'll just say we remember, these J plus and J minus in general satisfy this, and J3 with the J plus or minus, A plus or minus, J plus or minus. These K operators, if I let this construction be how it is here, I get K plus K minus is actually minus 2 K3. And the reason I use minus is because if I use this construction here, I get a fully negative result. And so I just define K3 to be in such a way that this works. And it generates K3, K plus or minus is plus or minus K plus or minus. So this is the algebra SU2. This is the algebra SU11, right? These are the 3 generators here. These are the 3 generators here for SU11. So that's what we're working with here. And so we were working on, okay, I have a decent idea of representing this here. But I get into kind of some tricky water when I try to use this construction here to get these back, right? And the idea is I'm trying to use the matrix representation, which still satisfies these commutation relations. And that works fine and dandy when I'm talking about, J plus, J minus, J3, J1, J2, all the J stuff works out nice. But it doesn't really work out as nice for this. Like if I have matrix representations which satisfy this, I don't get as nice of a thing. But there were some interesting observations made that are probably not coincidental, but are interesting. One thing I want to notice is that with my y equals AB here, so I'll just say in general, y equals AB, I construct something almost like, I don't want to say it's like a metric, but it's almost like a metric. It's a matrix that is of interest. So it's basically a matrix where my input is defined by y, and I'll say what I mean. So each ijth component of my matrix, I define as being yi, yj dagger. Cool. What do I get when I do this? Well, for instance, if I use this one, then my elements would be, this would be a dagger, this would be a b dagger, this would be b a dagger, and b dagger. Cool. And given this commutation relation, which we defined earlier, this spits out the identity matrix. And it spits out the 2 by 2 identity matrix. So that's pretty interesting. I get this thing right here. And so what if instead I take a different, what I'll call a vector, or a different column here. And so I'm going to call this E. The reason being is that doing this on it generates the Euclidean metric. So that's why I call it E. That's just my notation for it. What if instead I consider what I'll call YH? We'll see why I call it YH. I let it be A, B dagger. So then YH dagger is A dagger B. And what if I do this instead with YH? So then these elements are different. This is going to be, this is A dagger. This is A with B. This is no. Yeah, this is B dagger with A dagger, and this is B dagger with B. And so instead, I get now like a hyperbolic metric. I could call this eta, or this is in general just sigma 3, like the J3. But I just call this in general eta. This is like a hyperbolic metric right here. And so that's why I'm calling this YH. It gives me like a hyperbolic metric.
Why would you call it a metric?
The only reason being, and I guess the only reason I'm calling it a metric is because like in Euclidean space, like we have just identity metric, and in a hyperbolic space, our metric in general, when we talk about the inner product, is defined to be something like this, or a non-positive definite metric in general.
But do we have here some
No,
inner product?
it's not actually, not yet, but we'll have something similar that I will call as an inner product, which is why I'm using this. But I don't officially use this terminology or anything. I'm just calling it something like that. So what happens if instead I use this to try to represent these? What do I get out of it? So we'll see, and this is where the lack of believing that this is a coincidence comes in. Say for instance, I want to do K plus. I can represent it as this YH dagger, sigma plus YH. Remember, sigma plus, I represent it as 0, 1, 0, 0 in this 2 space. So this would be A dagger B, 0, 1, 0, 0, A, B dagger. And this comes out to A dagger, B dagger, which is the same thing as what I said K plus was over here. Yes.
Sorry, it's been a while. Can you again remind me what X hat is?
X hat is just an operator.
Okay.
It's just if I have an operator with a matrix representation, I want to re-represent it using these oscillators. So I can get K plus that way. I can also get K minus this way. I do YH dagger sigma minus YH, I end up getting AB, which is the proper one here. If I tried to use this standard one right here, there's no way of combining it this way that would be able to spit out an A dagger, B dagger, right? Remember both the A dagger and B dagger were over here. This was non-daggered stuff. So it'd just be some combination of daggered and non-daggered rather than both totally daggered or undaggered. So that was an interesting observation, one that we had. And then the next, and this is like perfect timing almost, the next interesting observation was what if I'm trying to represent the third components here? And so I'll just write out what J3 and K3 should be given these are my J plus and minus, and then these commutations are satisfied. I get J3 is 1/2 A dagger A minus B dagger B. And I get here K3 is 1/2 A dagger A plus B dagger B plus 1. So these pop out from these commutation relations. These are the results that we get. And let me clear my space here. I instead consider something like an inner product, which you're just talking about. So I'm going to define two versions of this inner product and I'll just use Y in general right now. So I'll have a Euclidean version of it, and I will have a hyperbolic version of it. This one is Y dagger 1/2 the identity. The 1/2 I'm just including because there's a factor of 1/2 here. That's what I'm doing. And then Y. And the hyperbolic, Y dagger, 1/2 this eta, where eta is 1, 0, 0 minus 1, and then Y. So it's like an inner product, right? My daggered object, my dual of it, and then here with some sort of metric sandwiched in between them. And so what happens if I use different matrices or different vectors to do this? So I'll write it over here, and this will be the final results, I suppose. If I consider the hyperbolic or the YH that I've written here with the Euclidean metric, then I get what's that? A dagger B 1/2 1, 0, 0, 1 A B dagger, and this does come out to 1/2 A dagger A plus B dagger B plus 1, where I note B dagger is B dagger B plus 1. That comes from the commutation relation that I just conveniently erased. So this is K3. And then if I take, and I'll write it over here. Actually, I'll just write it below it. If I take YE with YE and take now the hyperbolic structure that I consider here, I get A dagger B dagger 1/2 1, 0, 0 minus 1 AB. That's 1/2 A dagger A minus B dagger B, which is J3. So if I take the vector and use the opposite or the opposing metric to define this kind of inner product thing, I get the third component, which was pretty interesting. So those are the interesting results that I've gotten. Not entirely sure why these are the case, but I think it's not just coincidental that these arrive like this. So, cool. that is all that I had.
Right, thank you.
Questions?
Do you know, okay. Do you know the scaling form of a given algebra?
I don't know.
Scaling form is actually an inner product or a form for associated to any algebra. If you calculate this case for JJ or for this KK, you have different Killing forms, and that's where one of them is kind of like Euclidean-like, and another one is hyperbolic.
Gotcha.
So that's what really is, the geometry behind this Killing form.
So
Interesting.
it doesn't kill anything.
No,
Killing
no.
is a person's name, right?
Really? Yeah. Okay. Yeah. Let me write that down. There's probably.
It's spelled the same though, killing, like.
Yeah,
But it will kill you, you know.
Oh,
But
very.
it won't kill you to learn.
it came up, we were looking at terminology and dictionary math, and some of which is not politically,
Correct.
yeah, well, okay, like from master-slave circuits, they try to get away from that.
With what? With what?
Master-slave circuits,
Oh.
right, they try to get away from that, and that's
No,
reasonable.
you're kidding.
But some people looked at killing and then they didn't realize.
Yeah. I have actually.
Because they're killing fields and.
I know, yeah.
Yeah.
Instead of strawberry fields. That would be much nicer. This is my question to you guys. Do you pronounce it really Jordan in English or Jordan? Because he was a German, right? So it should be really Jordan.
We're not German, so we say it.
Yeah.
But he was. He might be not.
I call it what. You just use, what word did you use for his country?
German.
Deutschland.
You say Jesus,
Yeah.
not Jesus. You say Jesus, not Jesus.
Yes, because his name was Joshua. No, his name was Joshua. Joshua. Joshua.
Yeah, yeah.
Okay.
Questions, comments, concerns, mentions of interesting lexicon.
Yeah. Any other comments?
Narrate.
Linguistic or mathematical or metaphysical?
This is just something that popped up that was super interesting. Like, oh, what if I do this and what if I do this? Oh, I get that. Okay.
So I am very happy that you're writing. It's very much better than people's.
Very neat.
All
It
right.
is neat.
Like the handwriting.
Your writing is.
I
Read it.
I teach, so I have to be legible. That's it. My handwriting has gotten a lot better in the past year and a half.
Oh, nice.
I encourage the students to gripe when they can't read anything, and it's turned out for the better for me.
Mine are very pathetic and just don't complain about it, so I carry on as usual.
All right.
Feel ready to go home
Thank you.
Thanks.
on Thursdays.
No, we have
It's been a
more.
very long
We have
day, you
another-
know?
Colloquium. Yeah.
Colloquium in 3 minutes.
Oh,
In 33.
33.
Yeah.
Oh,
Yeah, I
yeah,
thought
yeah,
we did
yeah,
read
okay.
And there's
three,
coffee
but
after,
it's
right?
3:30.
Oh, is it? Did you make it?
Something.
Someone made it this
Oh.
morning or yesterday.
Yeah.
It is warm
Oh,
though.
okay.
I think it's time
What,
saving.
Dale coffee? It's a good.
Yeah,
It's good.
here's the PowerPoint.
Let's
A little bit of bacteria.
Yes, I don't see it.
no, there's no coffee, so I'm gonna have to apply.
Be invited though?
Who the hell emptied
should
out the
probably
I'm
forgot.
gonna kill
So,
them. Let's make
You
more.
like to show me something, right?
It was me.
Oh, yes. Yeah, we agree. Yeah.
Okay.
Oh, so it seems right.
Yeah, I assume so, yeah.
That's fine.
I love.
No, I love saying hello.
You can
Rob.
pause it or stop it. Oh, yeah, just stop. Yeah. You're getting out.
Choose avatar.
If you're just wondering,
Ooh.
Just
Can
kill
we
it.
mention?